Did you know Earth wasn't always blue? The oceans that now cover over 70% of our planet's surface weren't there at the beginning. Imagine a young, chaotic world where rivers of lava flow endlessly, and the atmosphere is a cauldron of toxic gases. So how did water come to exist here? Did it emerge from the depths of the Earth, or was it delivered from outer space? This is one of science's greatest mysteries, and the answers take us on a journey that began billions of years ago in the early days of the solar system. In this video, we'll explore this incredible story, connecting the dots between science, geology, and the cosmos itself. To understand the origin of water on Earth, we must go back to the beginning, 4.6 billion years ago. At that time, the solar system was a giant cloud of gas and dust called the solar nebula. This cloud began to collapse under its own gravity, forming a young star at its center, the Sun, and a disk of dust and gas around it. It was within this disk that the planets, including Earth, began to form. As this dust coalesced into planetesimals, the process created heat through friction and radioactive decay, further shaping the conditions for planetary formation. The inner planets, including Earth, formed closer to the Sun where temperatures were highest, meaning they were mostly rocky and devoid of lighter gases like hydrogen. This region was referred to as the dry zone, where the heat from the young sun evaporated most volatile compounds, including water. This highlights the mystery of how a planet in such an environment could eventually become water-rich. Planet formation happened in stages. First, microscopic particles of dust collided and stuck together, forming larger bodies called planetesimals. These planetesimals collided repeatedly, eventually creating the planets we know today. During this process, essential elements like hydrogen and oxygen were already present in the protoplanetary disk. However, Earth was far too hot to retain any form of liquid or frozen water on its surface. The temperatures were so extreme that any water molecules that might have formed would have been quickly vaporized or ejected into space. One fascinating theory points to the depths of the planet itself. During Earth's formation, minerals in the mantle trapped small amounts of hydrogen and oxygen. As the planet cooled, volcanoes erupted, releasing massive amounts of gases into the primitive atmosphere. Among these gases was water vapor. Recent studies suggest that a type of mineral called ringwoodite, found deep within the Earth's mantle, holds significant amounts of water in its structure. If these reservoirs are as extensive as some scientists believe, it could mean that Earth's interior has enough water to fill oceans several times over. This hidden ocean within the planet underscores the idea that the Earth itself played a massive role in creating the surface water we see today. This process, known as degassing, was crucial in transforming Earth's atmosphere and creating conditions for water to accumulate on its surface. Volcanoes not only released water vapor but also other essential compounds like carbon dioxide and methane, which helped retain heat on the planet, preventing all the water from evaporating into space. Recent studies have shown that even modern volcanic eruptions release water from Earth's interior, proving that a significant portion of Earth's water might have originated this way. Here begins the second chapter of the story, water brought from elsewhere. During a period known as the Late Heavy Bombardment, between 4.1 and 3.8 billion years ago, Earth was bombarded by a relentless shower of asteroids and comets. These celestial bodies were rich in water ice. When they collided with the planet, the heat from the impact melted the ice, releasing water that accumulated on the surface. The evidence for this theory lies in isotopic signatures. Water on Earth contains specific ratios of hydrogen isotopes, including deuterium. These ratios closely match those found in some types of asteroids known as carbonaceous chondrites, supporting the idea that these ancient space rocks delivered a significant portion of Earth's water. Comets, too, likely played a role, though their isotopic signatures differ slightly, indicating multiple sources contributed to Earth's water supply. These impacts were far from rare. Young Earth was located in a region of the solar system where collisions were common due to gravitational instability caused by the gas giants, like Jupiter. Jupiter played a particularly intriguing role. Its gravity acted like a slinger, redirecting many asteroids and comets toward the inner solar system. This cosmic traffic not only brought water, but also organic compounds that would later be crucial for the development of life billions of years later. Now that we understand the two main pathways that brought water to Earth, internal and external, it's clear that both were essential. Without the initial release of water from Earth's mantle, our planet wouldn't have started forming oceans. But without the impacts from asteroids and comets, Earth likely wouldn't have nearly as much water as it does today. What's even more fascinating is how these two sources influenced each other. The early water from volcanic degassing could have created temporary lakes and pools, providing a surface where ice-rich asteroids and comets could deposit additional water. These surface interactions helped stabilize the water cycle, allowing Earth to retain its water despite the harsh conditions of the early solar system. This interaction between internal and external sources also explains some unique characteristics of Earth. For instance, the water in Earth's mantle is chemically different from the water in the oceans, suggesting they didn't originate from the exact same sources. Simultaneously, the presence of hydrosoluble minerals in Earth's crust highlights the critical role of external impacts in supplying additional water. Earth is essentially a mosaic where internal and external sources perfectly combine to create a habitable planet. But why does Earth have so much water, while our neighbors, Mars and Venus, have so little? The answer lies in Earth's unique location and conditions. Earth is in the so-called habitable zones of the solar system, where temperatures allow for liquid water to exist. The presence of a strong magnetic field also played a vital role. This field protected Earth's atmosphere from being stripped away by solar winds, a fate that likely befell Mars. Without this magnetic shield, much of the water vapor released by volcanic activity or delivered by comets could have been lost to space. This protection allowed Earth to maintain the necessary conditions for water to persist. Another essential factor was the presence of plate tectonics, a phenomenon unique in the solar system. Tectonic plates help recycle water between the surface and the mantle, ensuring it remains in balance for billions of years. Without this process, much of Earth's water could have been lost to space or permanently trapped within the planet's interior, as happened on Mars. The combination of the habitable zone, Earth's magnetic field, and tectonic plates made Earth a perfect haven for water and, consequently, for life. And here we arrive at the most incredible connection. Water was essential for life to emerge. In Earth's early oceans, organic molecules began combining, forming more complex structures that gave rise to the first living organisms. That's why, when we search for signs of life on other planets, we look for water. It's the link that connects chemistry, biology, and habitability. Recent discoveries about extremophiles, organisms that thrive in extreme conditions, further highlight water's importance. These creatures live in boiling hot springs, deep-sea hydrothermal vents, and even under thick ice, proving that liquid water can support life in almost any environment. This has expanded our understanding of where life might exist in the universe, from icy moons like Europa to distant exoplanets. But water was also essential for life's evolution on Earth. The cycles of evaporation and precipitation enabled the development of terrestrial ecosystems, while ocean currents helped redistribute heat and nutrients, making the planet more livable. Additionally, water's ability to dissolve chemical substances created a dynamic environment for biological reactions, something no other known liquid can replicate. The story of water on Earth is an epic saga blending geology and astronomy, science, and mystery. It began billions of years ago, with materials coming from both the planet's depths and the vastness of space. Without it, Earth would be just another rocky planet, lifeless, without oceans, without us. So, the next time you look at the sea or even a simple glass of water, remember, you're looking at something that was once part of a stellar explosion that traveled billions of kilometers through space, and that shaped the history of our planet. If this fascinating story made you see water differently, don't forget to like this video, subscribe to the channel, and share it with your friends. Let us know in the comments what impressed you the most about this epic journey. See you next time.